Hello, everybody. How's it going tonight? My name is Quinn, and today we're talking about multi-agent reinforcement learning. There's a little research project that me and Ariel Kwiatkowski and Ben Greenberg work on to avoid the tragedy of the commons in simulations of multi-agent reinforcement learning. So this is me. I am going to introduce myself. I have a couple slides there. This is my socials. You can find out about me, and I also have my Calendly that you can, if you're really interested in like maybe some one-on-one time, you can also look up my Calendly. But here's my email, my website, my LinkedIn URL, and my Discord. For this is for DMs. So where I'm coming from biographically is years and years and years ago, I was a musician, as a matter of fact, and that was in Philly. I was a math major at CCP. I was in Lambda School's first data science cohort, and later I was a teaching assistant there. I had a Python job at a startup in 2020. In 2021, I participated in the AI safety camp, and here's the URL there. By the way, in the repo, which I hope you all have because it's on meetup.com, in the repo, if you go to biblio.md, you can get all the hyperlinks that are in the slides. So yeah, that's what I did in 2021. That's how I did the research that I'm talking about today. And earlier this summer, I was a research intern at the Stanford Existential Risks Initiative. And I'm currently doing formal verification at a consultancy validating a decentralized finance product, which is in the Cardano ecosystem. It's blockchain. It has nothing to do with data science. But I have many hats, and I'm a jack of no trades, as it were. Where I'm coming from, like intellectually, is much more simple. It's just, one, there's the principle that computers ought to be good for civilization. Two is the principle that AI advances could be really, really bad or at least suboptimal. And three is like, what leverage do we think research can have? Like, what can we do as researchers? And yeah, I have someone unmuted right now, but that's okay. I think they're so on the agenda today, what is reinforcement learning? What is a common resource problem? That's the tragedy of the commons thing. What is multi-agent reinforcement learning, or MARL? And how easy is it to spin up with Ray and RLlib? So that's just a library that I use. It's on top of NumPy and a bunch of other things. RLlib is a subset of Ray. Ray is a ginormous project. And this is a little bit misleading as an agenda because we'll actually be talking about Ray and some code samples and how to run them in the middle of like what is reinforcement learning section. So it's not like we're saving the Ray and the RLlib stuff till the end. So there's code examples tailor-made for the talk at this repo, and you can get access to that on the meetup page. I hope someone posts it in chat. And the research code that I did at AI Safety Camp with Ariel and Ben, that's in this repo, and that's also in the Biblio. So what is reinforcement learning? So let's begin. It's a very simple idea. It's not the most simple idea. There are simpler ideas, but it's a pretty simple idea. It's just you represent environments as states, actions, and rewards. And so if you take an environment and you say, okay, I think I can break this up into states where someone takes an action and gets a reward, then you might have a reinforcement learning problem. We solve these environments, so-called, by selecting actions to maximize reward. And the study of these solvers is called reinforcement learning. And that's basically it. It does get a little bit more complicated when you bring deep learning into it. Deep reinforcement learning is where you get like AlphaGo. It's where you get a lot of like self-driving car stuff. But the basic reinforcement learning isn't directly to do with deep learning. Okay. It's the basic reinforcement learning is just representing stuff as environments. Deep learning comes in when you want to come up with a function that takes states as inputs and selects actions as outputs. Well, states and rewards as input and selects actions as output. So the function approximation angle is where the deep learning comes in. But we're not even really talking about that much because what we're doing today is we're letting Ray handle that. Okay, so what Ray is going to handle all the deep learning for us. We don't need to think about that at all. So this is a classic example. It's called cart poll, and I don't have a video. I don't have an animation, but basically this cart slides back and forth, and there's a pole that swivels 360 degrees. And when you're basically, it's good when the pole stays up, right? So you can see if the pole is swiveling by shaking the cart back and forth in exactly the precise way, you can keep the pole upright. It's basically as simple as that. So what we're going to do is we're going to play a game where we're going to look at this environment. We're going to say states, actions, and rewards. Okay, what are the states? What are the actions and rewards? So I'm going to actually give you like 10 to 20 seconds to think about this. Like, think about this problem. It's an environment, right? The agent is really just the cart's like XY position. And what are the states? What are the actions? What are the rewards? And there's not like a canonical example. I mean, there's an example that's in the GYM library. GYM is a major reinforcement learning library that OpenAI put out. And there is like a canonical, I guess, interpretation in that library. But you can interpret this multiple ways. So if you don't get what's on my slide, you still might be right in a sense. So I'm gonna give 5, 4, 3, 2, 1, and we're gonna check this out. So the states are the angle and the horizontal position of the pole. The states are the angle and the horizontal position, the angle of the pole on the cart and the horizontal position of the cart. The actions are a delta in angle and a delta in horizontal position, except I don't think an action is a change in angle because you don't change the angle directly. You change the angle by proxy by horizontal position. So you by wiggling the horizontal position. So by wiggling the cart, you change the angle. So this is actually incorrect. So you don't actually change the angle. You just change the horizontal position of the cart. Your wiggle in the horizontal position of the cart is the only action you have. The state transition function is just a physics simulator. And the reward function is basically a large negative reward for the pole dipping beneath the ground line, 0 or small positive reward for the pole staying up. So that's how you model it. That's basically what goes on. That's how you model environment for reinforcement learning. So from a code perspective, there's a library called GYM. OpenAI put it out a number of years ago. It was like one of the first things OpenAI did as an organization, as a matter of fact. And it created this thing called the step reset paradigm. And it's been hugely influential. You know, most reinforcement learning code that you see is in this step reset paradigm. So what it is reset initializes the environment and returns the first observation you see. And step returns a for tuple, okay? A for tuple that has the observation, the reward, and just a flag that says whether or not you're done, okay? It also has this info dictionary that you don't even really need to use in most applications, in many applications. And this gym.space thing is an object. It basically comes in 2 flavors. You have box and you have discrete, okay? Spaces.box is for continuous action or observation space. And space.discrete is a discrete thing, which is really just numbers, because if you have any discrete finite set, it's equivalent to the labels being just natural numbers, right? So discrete means you can't split it up infinitesimally, and continuous means you can split up infinitesimally. So if ints are discrete, floats are kind of continuous. Floats are basically model continuous. So that's the step reset paradigm. So we're going to get into some code here. This is a guessing game that I wrote with the step reset paradigm. So what I do is I import gym and I import gym.spaces. Both my observation space and my action space are both discrete. In fact, they are equal. And this is a very simple game. What you do is you select an action that tries to guess what the state is, like right now. But the state is completely random. You see observation space.sample. Remember, the first component of the tuple that returns from step is an observation. Observation space.sample just selects a random one. So this is a game that is so trivial and so random that it actually can't really be played meaningfully. You're never going to get better than chance in this game, but it shows the step reset paradigm. So the return of step is the next observation, which is a sample from the previous observation. The float is just if my action equals the previous observation. So if it equals the previous observation, then I get a 1. If it does not equal the previous observation, then I get a 0. Okay, that's all it is. That's all that happens. And the remaining rounds is less than or equal to 0. So see, it decrements remaining rounds. And when that gets to 0, you're done, right? So that's why the done flag is this Boolean value, this Boolean expression. So in the guessing game, so let's see if you could think of this. So we have states equals actions. So the states and the actions are the same. And in the n equals 2 case, it's just 0, 1. The state transition function is a random mapping from 0, 1 into 0, 1. A state transition function in reinforcement learning actually does take the action into account. But this one doesn't, because this one's so vacuous, it's so random that it doesn't even take the action into account. And the reward function is anything that takes from states cross actions, which means the tuples, right? So the cross here just means the tuples of states and actions into 0, 1, such that reward of a state and an action is equal to 1 if the state equals the action, and 0 otherwise. So it's basically that. So let's play. If I go into my shell here, I didn't initialize my shell, so it's going to take a second. I just need all my software installed into my virtual environment. And initializing the shell takes a while because of the way I did it. But this is basically what Ray code looks like when you're actually training. Okay, so PPO is the name of a major reinforcement learning algorithm. It's so famous because it has good performance and it's agnostic whether its actions and observations are discrete or continuous. But it has really good performance in a wide range of cases. So it's really just an import for us. So what RLlib does is it provides PPO. And what you do is you pass in PPO.trainer and you pass in the environment that was a subclass of gym.env. If you recall, guessing game subclasses gym.env, right? So that's why it's a valid constructor to pass into the trainer, and the config just takes the arguments. So this is the n equals 10. We discussed on the previous slide the n equals 2 case. It's still running. It won't take much longer. I had it set up to do some validation every time I initialize the shell, and I forgot to initialize the shell before the talk. But that's basically what it's going to look like. And you just do trainer.train. Okay. So Ray makes it so easy. Ray is the ideal thing if you're in a situation and you're saying, hey, you know what? I think I can represent my environment as states, actions, and rewards. Okay, you don't have to be a reinforcement learning expert. All you need to do is these very few imports and this relatively simple subclass. So the possibilities are endless. Here we go. Okay, so we're going to do Python main.py game equals guessing game and n equals 10. So this is going to run a little bit. I can make it bigger. Let's see if I always forget what the flag actually is in the game argument. Yeah, it's just a G. It's not guessing game. It's just guessing. So this is going to run, and Ray is going to initialize. Yeah. Are there while this is happening? Actually, I don't think it's going to take that long. So I was going to. Yeah, I think this is already gonna. So at n equals 10, it's a guessing game where there's 10 states and 10 actions. So what do we think is going to happen in the average reward we're going to get? What do we think is going to happen in the average reward? Just think about it. And this is the first exercise of the talk. So yeah, you can see it's logging a bunch of stuff. It's a pretty verbose tool, but that's good because it's really easy to work with like GPUs. It's really easy to work with clusters on this. So the output, if you recall in the code, I do print trainer.train. So I print the output. The output of trainer.train is a dictionary. And I know how to read this because I'm experienced. So episode reward mean is 100, right? And isn't that expected? Because one, it's early in training. So, but even, I mean, with this game, it's too random. So we're never going to do better than chance. You basically have a 1 in 10 chance of being right. So in a thousand episodes, the episode length is 1,000. We got 1/10 of 1,000 is the mean, right? So that's basically what we would expect. Okay, so I'm already at 626. So yeah, navigate outside and open up CLI. I already did that. So this is the part of the talk where we get into common pool resource problems. But that's your basic introduction to Ray for the single agent case, and we will be returning to Ray for a multi-agent case after we talk about this particular kind of problem. So we're going to talk about economics for a little bit. So common pool resource is a rivalrous, non-excludable good. And it's like timber, it's like fish stocks. So you can, if you stare at this a little bit, like you'll get it. Satellite television is excludable because you can like keep people who don't have a subscription out, but it's non-rivalrous, which means the more people who have satellite television, roughly speaking, the product doesn't necessarily get worse, right? So that's why it's non-rivalrous and excludable. The complete opposite of that on both axes is a common pool resource. It is non-excludable, which means people have public access to it. It's like a public kind of thing. It's rivalrous, which means you're in competition with other people for it. So that's a common pool resource. So CPRs that's what I'll be calling common pool resource problems. Will be CPRs. Okay. So a CPR forms an approximate prisoner's dilemma, and I'll talk about what that means. A prisoner's dilemma I will abbreviate with PD. So a prisoner's dilemma, or a PD, is a type of game where each of two players can make one of two moves per round, and there are payouts. Okay. However, there's lots of games that fit that description, but this is a game that is distinguished by the property that the most stable tendency is toward the worst outcome for each player. It's actually not the worst outcome for each player. I actually misspoke when I wrote this, but it's the worst total outcome if you sum up the rewards of all the different players, of both players. So it's the worst, in aggregate outcome. It's the worst collected outcome. It's the worst outcome for the collective. So this is the canonical prisoner's dilemma. Basically, you have a a warden who makes an offer, to make a deal with two prisoners. But the thing is that the warden makes this offer to the two prisoners separately in different rooms, and the prisoners have no knowledge except for the fact that the other prisoner has the same offer. And the prisoners aren't communicating about this, right? So the idea is in cooperate, where both prisoners cooperate, they each serve 1 year. And that's like a payout of -1, where prisoner player A gets payout of -1, player B gets payout of -1. You can see if you're following along, you can see that prisoner A gets 3 years and prisoner B goes 3 in this outcome, and that's represented by -3, because a game can be thought of like a matrix of tuples. So the worst outcome in aggregate, right? Not for an individual player, but for both players as a collective, is -2, right? Because the sum is -4. That's as low as the sum can possibly be. As high as the sum can possibly be is -2, right? So in a way, we think that this is the best equilibrium, right? As if they're both cooperating. However, that is not an equilibrium, because that is not where the energy of the game the free energy of the game kind of points to, right? What the game points to is one of them defecting and then both of them defecting. So that's why we call this -2 outcome a Nash equilibrium. Equilibrium is the kind of fancy word. Nash is just named after the person who came up with it. So here, we're just going to take a little break here. And this is going to be something where I think, let me see, how many people do we have? Yeah, 23. Let's do even unmuting to discuss this is something I'm happy with. I guess I didn't discuss that with the organizers, but yeah, convince yourself that -2 is the most stable outcome, even though -1 is the highest sum reward. I hope this makes sense to people. And if you can identify your confusion, I would invite you, if you're up for it, to unmute yourself and describe your confusion. And otherwise, we can move on to the next one. Imagine a lake with with fish and 10 fishers making a living catching them. In what sense is a PD a useful model? So I do want to give some moments to think about this. And I am sensitive on what time it is and how many slides I have left. But I just want to give you some moments to think about this before I tell you the answer. This is something that the literature has enjoyed doing for a while, is modeling common resource problems as prisoner's dilemmas. So I hope it's kind of clear. So I'm going to take, we're just going to take 30 seconds and sip some of this late night coffee. So you can think about this.
I guess we could maybe make a comparison if the fisher people if the fishers are like surrounding the lake and, one starts catching a fish, are they going to let the others know, hey, there's fish on this side of the lake? Or are they going to stay silent and just kind of see what they get? Maybe not knowing if there's even more fish on the other side of the lake near other fishers. Does anybody else have any ideas?
I would say that when it comes to the fish, obviously he already leaked the result, Tragedy of the Commons. And what happens there is if the fish are taking enough, each fisherman has a choice in how much fish they take. They can choose to take enough so that there will continue to be a supply of fish. However, if people decide to go into prisoner's dilemma mode and only care about what they take, then eventually the fish become depleted. And once you have that breakdown, especially with a common resource, when people notice that someone is taking more, either they have to employ some external strategy to get them to not fish excessively. So either they would regulate that, or everyone ends up taking the fish. And then, because if you don't take the fish, someone else is going to take it and you're not going to get anything.
Bingo. 200% Melvin. that's kind of the dilemma. That is why we believe, as this is why the literature tends to believe that Prison's dilemma is a useful model. Okay, so one of the assumptions of game theory itself is that the players are not communicating, but they are aware of the payoff matrices. Okay, but players are not communicating in any way. So clearly that will break down in the real world. But Melvin got the basic idea behind why Prison's dilemma is a useful model in this scenario. So another thing the literature says is if you're trying to be sustainable and no one else is trying to be sustainable, is you're a sucker. Okay, that's the word the literature uses. Is you and no one wants to be the sucker, so that's why everybody will neglect to do the sustainable thing, even if they thought of it. So this outcome, the literature tends to call it the tragedy of the commons, and it's a little, it's a little dated in a sense, and mostly because of an economist called Elinor Ostrom, who was kind of trying to get people to not kind of use this like conclusion like too much. So one example is if you believe that CPRs will always lead to tragedy of the commons, no matter what, is you will say, okay, we need to privatize the resource, or we need some like external administrators to come in. So in her book, or one of her books, she talks about like these colonial administrators in these various parts of the world. I forget where exactly, but they were like, oh yeah, surely we must come in here and tell these people how to divvy up this resource, or else they'll get a tragedy of the commons. So this was used to justify policies for a long time. But Elinor Ostrom was this economist, and wrote this book, which I read, Evolution of Institutions for Collective Action. And I have a little review of it. It takes like 3 minutes to read on my blog here. So she did an empirical study, right? Actually going out and observing comparable resources in the wild, and reporting on the sort of mechanisms that had emerged. Okay, so there were these emergent mechanisms. And I'm actually going to go through all these. This slide has just too much room, but you can read about this all right here on Wikipedia, and this is in the bibliography for the talk, which is in the repo. But there's basically principles for sustainable and stable solutions to emerge. There are principles that she kind of characterized by doing like a broad empirical kind of project, like all over the world. Just a lot of like talking to people and looking at logs, and that's the kind of work she did. I'll just summarize some of the insights I got the book. One is the skin in the game principle. Things tend to work when the design process is not like offloaded to people who aren't directly involved, right? Like the fisher people themselves tend to do the best job at designing mechanisms for how to divvy up the fish. Local knowledge, stuff about the environment that an administrator would not know, plays a huge role. And also the reputation, which is like a way I think that like people kind of keep track of what each other do, is kind of like one emergent property that definitely plays a role, I think, in my reading of the book. Okay, so so that's basically the insights I got from the book. It informed the research question I would pursue with my team at AI Safety Camp. And we're going to talk about that in a second. I have one more toy game to introduce: multi-agent reinforcement learning in Ray. So we're back into code now, and I might pull this up in Emacs because this code is a little bit more complex. But it's basically rock paper scissors, okay? But it's rock paper scissors generalized. So if I have rock paper scissors and a fish, that's 4 things. If I compare paper beats rock, scissors beats paper, and then fish beats scissors, but the comparator is atransitive, so fish doesn't beat paper, and fish doesn't beat rock. In fact, since there's only four, it'll wrap around, and then rock will beat fish. And then you'll get a 0, a -1, or a 1. So it's this generalized rock paper scissors. I still call it rock paper scissors, but it's generalized. And so I have an atransitive comparator, and I compare it with the double less than sign. So basically, multi-agent reinforcement learning in Ray and Jim is the step reset paradigm, where for observations, you return a dictionary mapping an agent ID to an observation. So each agent gets a separate observation in multi-agent reinforcement learning. Well, I mean, in some ways of doing multi-agent reinforcement learning, but this is sort of like the way the software wanted to do it. Its reward is a dictionary mapping strings to floats. And so this dictionary maps strings to ND arrays because I use box. Okay, so box for the observation space, remember gym.spaces.box is the continuous observation signal, and it takes the form of arrays. So an array is an element of box, right? Of gym.spaces.box. And it's basically the observation gets returned as the first element of the return in step. And the reward is similarly, it takes the agent ID as a reward, as the left part of the map, as the keys of the map, I should say, and it takes the reward as the values of the map. And then it takes a done signal. It's just a dictionary from strings of bools. So different agents can be done at different times. That's not how I'm doing it. I'm just doing this in a very simple way. But different agents can be done at different times. And then it returns a info, but don't worry about info. It's kind of pointless. So that's the return type of step. So you see I initialize on an array of zeros, okay? And I return, where is my observations? My observations is agent ID of what basically I got against every other agent. What I got against every other agent, okay? What my move gave against every other agent. So that'll be a 1, a -1, or a 0. Will be an observation, and then the reward will be the sum of all those. So this is a simple case where the reward is the sum of my observations. So we're going to play the state's actions rewards game again, but think of it as like one agent at a time, right? So when I wrote this in Ray, I had to, or Jim rather, I had to use dictionaries to keep track of all the agents at once. But now I'm just going to think of it as one agent at a time. So the states is an array of what everyone did in the previous round relative to you. That's what the observations were. The actions were rock, paper, or scissors, but generalized. So like rock, paper, scissors, fish, rock, paper, scissors, fish, pizza, like whatever. The state transition function is each agent's other decision, because there's not really just a distinguish between, I mean, the observation, the rewards are the sum of the observation. But you can see that this is going to be across agents, it's going to be zero sum. So when we play this game, Python main.py game rock, paper, scissors, and let's do n equals 10. Does anybody have any guesses what's going to happen here? So what we're going to do is, just as we did up here, is we looked at episode reward mean. The episode length mean is again going to be 1,000, okay? But we looked at episode reward mean. And we saw it was, so this is another game that is so random as to be unlearnable, right? I wouldn't want to train this to see if I could improve performance because my game is too random, too much randomness. But it just illustrates the code. It doesn't illustrate how to model a problem. Think about what you expect and register your prediction with yourself, maybe by like writing it down on a piece of paper, what we think the reward mean is going to be. So what the reward mean is going to be the mean reward mean across all agents. Okay. And what it's going to come out to is that is kind of predictable if you think about it, but I might not have like explained the environment enough for you to be able to predict it. So you can see it's taking a little bit longer. I also have like no CPU on this machine, by the way. I run on like low CPU. It's kind of funny, but I don't have GPU going on. So, but yeah, it's going to happen a little bit. Keep thinking about what you expect the episode reward mean to be. Any second now. What's my next slide? Okay. And I'm at 1845. The suspense is terrible. I hope it'll last. We don't need to see this. So, yeah, what's going to happen is the episode reward mean is going to be 0 because this game is so zero sum and no agent has any ability to learn anything. So the episode reward mean is going to be 0. And I'm basically just going to cancel this so it doesn't overheat my machine because we're not even going to see the output. Okay. So what is the CPR reputation research section of the talk? So this is what I did at AICFG Camp 5 with Ariel and Ben. So our basic research question was derived from my reading of Ostrom. It's does moral simulate tragedy of the commons? 1. And 2, can we design or simulate a mechanism to dodge tragedy of the commons? So there's a lot of it. There's a lot of code, I mean. We actually wrote our own grid world engine, which I actually don't recommend doing. Like you can probably find a grid world engine to suit your needs. Like you don't have to write your own grid world engine. But we wrote our own. And you know, we had a good time. So but it took us like way too long. So it is on GitHub for you to read later. It's in the bibliography. So we aren't the first people to ask the basic CPR and tragedy of the commons and multi-agent reinforcement learning question. Okay, so there's actually like 2 or 3 papers, mostly from DeepMind. There's like 4 or 5 papers actually that are in the realm of like sustainability science and multi-agent reinforcement learning. So we basically implemented a grid world game about collecting apples. And these apples replenish for an arbitrary number of agents. So it's basically you'll see in the next slide. I only have one video, but we had metrics like sustainability and fairness, so we could measure how much sustainability was in the environment in a given play of the game. So we did this with RLlib. Okay, what's going on here? Okay, this is just the ODP file not importing a video very well. So what I'm going to do is I'm going to open up the video. Multi-term, cd ... CPR reputation, ls. Okay, they're all here. My videos are all here. Okay, here we go. Everybody see? Wait, did we see the video?
Yep, I can see it.
Okay, so this is our grid world game. The green stuff is the apples, and you can see they're replenishing until their cluster gets exhausted. Okay, so it's just like a fish kind of thing, because fish reproduce until they're exhausted, right? So the apples regrow until they're exhausted. The game ends when the apples are all gone. And what we did is, so in this version of the video, you can see all the bright red is our tagging mechanism. So what we did is we followed the DeepMind paper and we gave the agents lasers. And the lasers disable other agents for like a certain number of time steps, like 50 time steps, or like 25 time steps or something. And what we replicated was you can get something pretty sustainable with just the tagging mechanism. Okay? So what we wanted to do was to implement a fourth dimension. So this observation space is 3 dimensions, and I won't get into the details, but it's basically gym.spaces.box, right? And it's an array. It's a 3-level array. It's like a tensor, and we added a 4th layer to that tensor to represent reputation. So when you would take an apple, when an apple was the last one in its cluster, you would lose some reputation points. And when you would see an agent with like a low reputation, might you be more inclined to tag them out because they're going to be irresponsible? They're going to be unsustainable. So that's kind of the sort of the idea behind the hypothesis. Oh yeah, I knew it wasn't going to work because I wrote down. I told myself to open up actual file from the terminal if it doesn't work. Okay, so our findings. So that was the idea. So we had this reputation system quasi simulated. We didn't really see very much interesting necessarily. We're not shouting it from the rooftops, okay? Like we replicated the papers. We saw some marginal improvements, but it wasn't the improvements that we wanted, okay? Not even so. The before and after vids don't really look very different. So before after vids don't really look very different when we added reputation. So what do you think happened? Did we not represent it adequately for the agent to act on it? Was the representation adequate, but our hypothesis wrong? I don't know. We don't know. So yeah, we replicated the tagging mechanism thing from the paper. The reputation did decrease utilization of tagging, okay? But it was negligible on sustainability and fairness. Fairness is like sort of the wealth inequality metric. The wealth, so we use like wealth inequality metrics, the Gini coefficient, to do fairness. Sustainability is just something to do with the apples. We do have the write-up, the report back, which has the graphs or the metrics against the control group. But like I didn't even put them in the slide because they're not like awesome. They're not like, whoa, you guys like found something. Like we didn't really find anything. Our mechanism design skills have been lacking, because that's all that really happened. But yeah, that's what we did. So conclusions. Ray is surprisingly easy. You can turn your ideas into experiments in a reasonable time frame. Science is about not always getting the results you want. So that happens. That's totally what happened. Yeah, doing high impact research is hard. Yeah, so I'd like to say thank you to DataPhilly, to the open source software projects, LibreOffice, which is where I did this slide deck, Python on Nix, which helped my virtual environment, and Ray, of course. I used a lot of Wikipedia, I always do. And AI Safety Camp 5 was great. You should totally sign up. They're opening up applications for round 6 soon. I can definitely talk more about that. So yeah, I'd like to thank all of these. And I'm just gonna close it on my my basic contact page. And thank you very much for listening. And that is the talk.
Quinn, I have a question.
Yeah.
When you say that reinforcement decreased tagging, or sorry, reputation decreased tagging, does that mean that having a positive reputation decreased the use of tagging, or just including reputation decreased the use of tagging overall?
Including the mechanism, decrease the use of tagging overall. We actually don't have that granular of, we don't have it that granular. We don't have like insight. This is sort of like an interpretability question. So interpretability isn't great for a project like this. And what I mean by that is we don't know if an agent was saying like, in my line of sight is someone with bad reputation, so I'm going to use my tagger gun thing, laser weapon. We don't know that that's what the agents were thinking. Okay, we don't know what they're thinking at all. So from an interpretability perspective is really where your question is coming from, and we don't know. We totally don't know. We just know that if you look at purple, the number of shots mean is lower than maroon, which is tagging with no reputation system.
So it's just the number of tags go down if you include reputation into the system.
Yep, totally.
Cool.
From a high level, we don't know. We don't know if it's like the causal link. We don't even know the causal link. And this is like the coolest result we have, because our other results are basically null results. They're saying that like control and experiment were basically negligible. Yeah. So I can open up the chat now. Yeah, the biblio.md is in the biblio.md is in the repo. So if you go into the repo, someone asked me that, I think it was a private message. If you go to the repo and you click this one, that's where it'll be.
So, so you said that the people, like the agents, are the best people that can, have to, like when you were talking about like the fish in the lake example, for instance, like the fishers are the ones with the most information available to them to contribute to the system. So how can something like this be extrapolated into actual policy? Like, can someone do like some sort of study and say, you know what, based upon our results, we think that some, people within a local community can make better decisions about resource management in the neighborhood than the state can, or something like that.
Yeah. Well, that's what like Ostrom's conclusion was. And if you think about it, like it's sort of like counterintuitive to bring that kind of thinking into reinforcement learning, because if, let's say, like a regulator contracted a bunch of computer scientists to do some like agent modeling with multi-agent reinforcement learning, the conclusions they would get would be invalid, by Ostrom's own advice, right? Or they would be like suboptimal or ineffective. Even if this research went like really, really well, it would still like not be leveraging local knowledge. So what would be a much cooler research project would be to see if, like, in AI world, the principle that local knowledge informs in a very positive way the mechanism design, would be to make an environment in which like they can design rules of the game. Making agents can learn to design rules of the game. That would be like way cool. That would be super cool. I don't know how I would begin to do that, but I would love to do that.
Yeah, I like that idea.
Yeah, no,
Just
but that's like a totally good question. So like the applications here, like what we thought, the reason we thought that this might be might be an impactful research direction was because like there is going to be like offloading of like negotiation of things and like delegating negotiation itself to AIs. Like that's probably going to happen in the economy. So like looking at ways that like, oh yeah, how do we reason about sustainability in a multi-agent reinforcement learning context? I think is could turn out to be pretty important. I'm not saying that this particular project would turn out to be important, but like the space of ideas in which it was working, I think could turn out to be really really important. I should probably add to the bibliography like a couple podcast episodes actually that deal with like related questions that you can check out. People also kind of thinking about this like AI multi-stakeholder scenario kind of crossover world. Yeah.
Has your group come up with any ways to fine tune this to where you might be able to get a better result from your reputation factor?
You know, we kind of, I don't know, we were like initially a little disappointed, and then we like were out of time in the camp, and then like we didn't invest more bandwidth or resources into it. We kind of like left it where it was instead of trying to push it. We thought it would be better to report that our results were disappointing than like just try to game the system until our results weren't disappointing, because we kind of thought that would be less useful of a result. So yeah, fine tuning it until we start to look more right is a reasonable kind of question. I just don't see us putting the time into that right now. Yeah, I don't know. It might not be a useless area to look in. So, I mean, cooperative AI overall is a very cool field to be in. I mean, like DeepMind is putting out a benchmark soon. That would probably be a better place to explore this like applied Ostrom kind of stuff. And it's also, frankly, it's going to be a cool place to go outside of multi-agent reinforcement learning because of decision transformer. So decision transformer is where they take a language model like a GPT and they train it on sequences of observation and reward signals, and they have it take actions instead of the architecture from a language model is a sequence to sequence model, right? And reinforcement learning can be thought of as sequence to sequence because it's a sequence of observations and rewards going into a sequence of actions. So leveraging that to sort of replace reinforcement learning with like transformers, which is the architecture behind GPT, that is a very promising direction. Which some people think that's where the literature is going to be going in over the next year or two, and that's something that I would want to explore if I would keep doing this. So if I would keep doing cooperative AI, I would not even use reinforcement learning. I would use decision transformer.
Very cool. It looks like we did have a couple of questions come through in the chat now as well.
Great.
So George is asking, what if agents form cliques in a social and or graph theory sense?
Yeah. So cliques in a graph theory sense, that's just a particular way to quantify like the intuitive idea of a clique. I actually forget exactly what I mean. But yeah, I can not even think about that because so in this environment, so you would have to program that in a sense. But that would be hard to program in, wouldn't it? Well, that would be fun because what you could do is find ways to opt into groups that sort of share reward signals. That share reward signals, and we can play with that. We could play with that, or one could play with that. it's not something that would emerge natively from this implementation. From the obvious Ray and RLlib implementation of this, it's not something that would emerge. However, if you look at the DeepMind paper, which I can put in the bibliography, I don't know why I didn't. Yeah, it's a biblio.md is a file in the repo. In the DeepMind paper, they create walls in the environment. So we only showed you open map, but what they have is they have walled off areas, and people would effectively like privatize and then police the entrance to their walled off area. And it sort of increased sustainability at the price of increasing the inequality metric. And so you could imagine a coalition kind of coming together to police the boundaries of a walled off area like that. And that actually could emerge without adding some extra banding together mechanism. So that's a pretty good question. That's certainly a research direction. But you would have to implement it.
Relly has a question. Would training longer have resulted in better findings, or did you find that nothing was being learned and would not get any better?
I mean, it's the same thing you do in any other, when you're training anything, is like you find the point diminishing returns. Right? Like you find like, you start to think that like, yeah, more training isn't really doing much. And you can see that on the graph. So we use weights and biases. Weights and biases takes a stream of your training like metadata, and it puts up like graphs in a web app that you can follow along, and you can look how the training is doing. So if it's training on like Ariel's machine, Ben and I can look at how the training is doing, all the metrics we're interested in, on weights and biases. And Ray actually makes it integrating with weights and biases really easy. And TensorBoard can do stuff like that too. But yeah, we really decided that like, yeah, more training isn't going to make this change, because like if you look at the graphs, well, this one looks like it's kind of has activity after 4K steps, right? But the rest of these, like they're not doing anything. They're not going to change, However, like that's also wrong. Like sometimes, like you've heard legends in deep learning history of like training not looking like it's going to go anywhere, and then leaving it on accidentally and going home for the weekend and coming back, and it like did something amazing after it looked like you were already at the point of diminishing returns. So yeah, I don't know.
I think those are all the questions we have. Thank you again. We're going to stop the recording now, but if you stick around, we can all network for a little bit. We can turn off video, say hi to each other, talk to Quinn more, etc. So let's stop the recording.